We'll continue our study of helicopter rotors in forward flight. We have looked at how the thrust vector need to be tilted forward so that the forward component overcomes the drag while the vertical component overcomes the weight. We developed a very simple inflow model according to Glovert, which is built on Rankine's actuated disk theory that we saw in hover and vertical climb. Then we developed an expression for the induced power, and we also developed an expression for the parasite power, and we developed an expression for the profile power. So we came up with the total power consumed by the helicopter as a function of the forward speed. We noticed that the power initially decreases from hover, then it starts rising at the rate of velocity cubed at very, very high forward speeds. So now we are ready to look at the forces and moments acting on the rotor, integrate these forces and moments to get the total thrust, total drag, all the moments and so forth. But before we do that, we need to select a set of coordinate systems. Unfortunately, there's not a single coordinate system that we could use. There are multiple coordinate systems that we can possibly choose. And most common are 3 coordinate systems. So we are going to talk about those 3 systems in this very short video. The first coordinate system is what we call a shaft-based coordinate system, or a hub plane sometimes called. So in this coordinate system, this is the shaft about which the blade is rotating. So the z-axis is pointing vertically upwards. So that's the z-axis. So this is the rotor seems to be rotating about the shaft. So z is coming towards us in the plane of the paper. X is behind the pilot over the tail boom. So psi equal to 0 defines the x-axis. Then because we are using a right-handed coordinate system, the y-axis is to the right side of the pilot at psi equal to 90 degrees. So x-axis is along the fuselage symmetry plane, normal to the z-axis. Y-axis is perpendicular to the fuselage in a symmetry plane and also perpendicular to the z-axis. So this is called a hub plane or a shaft plane. So when you talk about alpha is the free stream velocity angle that makes with this disk. So that particular alpha will be called alpha shaft or alpha sub S. S stands for shaft. Okay, so this is one of the 3 coordinate systems that is often used. In this coordinate system, the only thing that stays fixed is this particular shaft is rotating. Other than that, it's the z-axis is fixed. But the blades are going to be flapping up and down. And the blades are also going to be sinusoidally pitching up and down as they go around the azimuth in an effort to produce roughly equal amounts of lift on the advancing side and also on the retreating side. That's what they would be doing. Now the second coordinate system is called the tip path plane coordinate system. In this coordinate system, you look at the tip of the helicopter blade. We assume the blade is rigid. For simplicity, we assume that the blade is connected to the shaft right at the center without a hinge offset. Then you draw a line when the blade is right behind the pilot over the tail boom. Look at the tip. Then look at the blade, same blade when it comes in front of the pilot in the symmetry plane of the fuselage. Look at the tip. Join these 2 things by a straight line. This is your x-axis. Now the z-axis would be perpendicular to this line. And then the y-axis by right-handed coordinate system would be going into the plane of the paper. So this is called the tip path plane. So the free stream, if it is coming this way from left to right, the angle between the free stream and this tip path plane would be called alpha tip path plane or alpha sub TPP. What's so special about this coordinate system? The main thing is in this coordinate system, the blade seems to be touching the rotor. The rotor disc is touching this plane. So if somebody is sitting on this plane, they would say, I don't see any flapping at all. When I see back here, the blade tip is touching the coordinate system. When I see in the front, the blade tip is touching the coordinate system. So in this coordinate system, the blade is not flapping at all. So flapping dynamics, flapping up and down, can be neglected, which considerably simplifies some of the algebra and also analytical integration work that we need to do. So a tip path plane is often used. It's a very common coordinate system in helicopter aerodynamics. You will still have the blades pitching up and down as they go around, but at least on this coordinate system, it seems as though the blade is not flapping at all. Blade is not flapping at all. So let's look at the angle relationship between the shaft plane that we defined previously and the tip path plane. So this is the rotor shaft. So that this is the shaft axis. So this is the shaft plane. Okay, this is this dotted line. Black dotted line is the shaft plane. Now, the beta of the blade is varying sinusoidally like this, flapping up and down. Beta is the flapping angle. So behind the pilot, psi is 0. So cosine of psi is 1. So behind the pilot, this angle is beta naught plus beta 1c. Now this is r. Then therefore the vertical height here would be r times sine of beta naught plus beta 1c. But for small angles, sine of theta is theta. Sine of angle is angle itself, as long as the angle is expressed in radians. Therefore, this vertical height is r times beta naught plus beta 1c expressed in radians. This is, by the way, we are only keeping the first harmonics. In reality, the blade may undergo second harmonics, third harmonics, even higher harmonics. There may be sine of 2 omega t, sine of 3 omega t, or cosine of 2 psi, sine of 2 psi, cosine of 3 psi, and so forth. But we are simplifying it for tip path plane. Performance step of calculations, first harmonics are the only ones that we keep. How about in front of the pilot? This is r. Psi is 180 degrees. Cosine of 180 degrees is minus 1. So this angle is beta naught minus beta 1c. So the vertical height is r times sine of beta naught minus beta 1c, which is simply r times beta naught minus beta 1c for small angles when these angles are expressed in radians. So this is this height. This is this height. So the difference between this overall height and this height is r times beta naught plus beta 1c minus r times beta naught minus beta 1c is simply 2r beta 1c. So this is this short height. Now this is our original shaft plane. In the shaft plane, this distance is still approximately r. This is r. So this is like a 2r. Okay, so the diameter of the rotor is 2r. So if this angle is 2r times beta 1c, then it follows that this angle should be beta 1c, because tangent of beta 1c is roughly beta 1c. Tangent is opposite side by adjacent side. Opposite side is 2r times beta 1c. The adjacent side is approximately 2 times capital R. Therefore, this angle is beta 1c. So what this tells us is that the shaft plane and the tip path plane will have an included angle equal to beta 1c when we are viewing it from the side of the helicopter. This is behind the pilot. This is in front of the pilot. We are looking at the helicopter from pilot's left. Okay, so that's what's going on. This is how the tip path plane will look from the side. What happens if you look at it from the behind the pilot, behind the helicopter? You'll get a similar expression, you'll find it is a beta 1s, okay, because the blade is flat. In the direction, it will be beta naught plus beta 1s to the pilot's right, beta naught minus beta 1s to the pilot's left. So the tip pad plane will have an angle of beta 1s from the left compared to the right. The last and final plane is called the no feathering plane. So the rotor has got something called a swash plate. There are two swash plates really. One is in the fixed coordinate system. It's attached to the fuselage. So the pilot or an autopilot takes some control actions. So they move this pitch link or the push rod up and down. When they do this, we are viewing the helicopter from the pilots to the side. Then this shaft tilts forward, backwards. It can also tilt sideways. Okay. So let's say that the front part of this pitch is going up. Then this is the rotating swash plate. So this part is rotating about the shaft, attached to the shaft. This is stationary. So in between they are separated by some ball bearings to reduce friction and so forth. Therefore, this is going up, and then when the same pitch length, when it comes 180 degrees later, it's going down. The way it is connected, when the swash plate goes up in front of the pilot, the connections are such that the blade to the pilot's right at 90 degrees azimuth will pitch up. Same way, when the pitch link comes down, the connections is such that the same blade, when it comes to the pilot's left, it'll pitch down. So we produce cyclical pitch up and down by a very simple mechanical device, a swash plate. So we have a pilot input. This is called a pitch link, and this is the blade's instantaneous position and cycle to 0 to 90 degrees at typical blade section. When the same blade comes, it should be the other way. The trailing edge will be, leading edge will be here, trailing edge will be here. So that will be the blade. It's cycle to 270 degrees. So in the feathering plane, this is called the feathering plane, or no feathering plane, I should say. So in this plane, these rods are not moving up and down at all because they are always touching this shaft, this one. So to them, the blade does not seem to be pitching up or down at all. So you're at an inclined plane. So this rod is not going up or down because you're lying down on this plane. So you always see the rod in contact is not moving vertically up or down. Therefore, in this coordinate system, the blade is not cyclically pitching up or down. So this is called a no feathering plane, or NFF. So this coordinate system is called a no feathering plane. So there are three types of coordinate systems: shaft plane, tip path plane, and no feathering plane. So the most common of these is either the shaft plane or tip path plane. Okay. So we will use both of them. In some of your homework, it's very easy if you choose the tip path plane for the next homework set and also for the quiz, second quiz. But you could have done the calculations also in the shaft plane. So these are the three coordinate systems that we need to be familiar with.